Hi and welcome. I'm trying to learn electrochemistry, electrical engineering, today electrochemistry, and after we've done it, we're going to do arm strength training. If you participate in the arm strength training, then it's better your own. This is part 2 of electrochemistry. In the experiment on conductivity of a liquid, using a mains lamp bulb as an indicating device, it is interesting to investigate water itself. Okay. I think the last part which we talked about was that water is a conductor. We had a name for it. To bring electricity or current through it. And if a lamp burns, then we know that it flows through it. And they said if we add sugar, it doesn't flow. And if we add salt, it does flow. It's an electrolyte. And we're using the lamp to know if it flows through. And now we want to know more about the conductivity of water. You will find that distilled water is apparently a non-electrolyte. In fact, a small current will flow through the water, but the current is far too small to heat the lamp filament. Okay. If the water is distilled, so I think that means that all what is in is out. Basically everything else without the actual water is out of it. So no salt in it, no sugar in it. Or what else would be in it? Then it does almost not conduct electricity. Tap water containing ions from dissolved materials usually will cause the lamp to glow faintly. Okay, we're saying water from tap which has some minerals in it makes the lamp glow a little. The addition of a few drops of acid or salt solution to the tap water results in a marked increase in brightness of the lamp. Okay, and if you add a type of acid or salt into the water, it conducts the water very good, the current very good, electricity and the lamp burns. Right. Okay, we're saying very clear water does almost not conduct. Water with some minerals in it, from tap water, conducts okay. But if there's salt water, then it conducts really good. So if there's something really in it. In addition of a few drops of acid or salt solution to the tap water, results in a marked increase in it. This information is interpreted as indicating that pure water is partly ionized. Among the molecules of water, a few ions are always present. About one molecule in 550 million is ionized. Okay, we're saying that pure water is a little bit ionized. One molecule of 1 in 550 million is ionized. And ionized means that it has one or one to less electron on the shell, so it was something like that. Briefly, an ion may be said to be an atom or small group of atoms which has gained or lost one or more electrons. Nevertheless, the ion present in the water, that is hydronium ions, H3O+, and hydroxyl ions, OH-, do have considerable effect on the products of electrolysis of some solutions. Some type of ions or some water that has an effect. Now we can consider the situation which exists in a voltmeter, the name given to any apparatus in which electrolysis is carried out. In a voltmeter is electrolysis carried out. If you had to know voltmeter was something completely different. Voltmeter, that was ammeter in voltmeters, and this is now a voltameter. Okay, a voltameter seems to be used to do some type of electrolysis, and this has something to do with, I didn't really get it, but we're talking about it now. The conversion of electrical energy into chemical energy. How perhaps. Now we can consider the situation which exists in a voltmeter. The name given to any apparatus in which electrolysis is carried out. I wanted to do actually right now a part about electrolysis, but then I noticed that we haven't read the chapter in which electrolysis is mentioned completely. I wanted to read it first completely and then go back to electrolysis. Now we're having a cathode and anode, a current in the voltmeter, and some types of electrolytes, and we're having plus, 2 types of positive ion moving to cathode, 2 types of negative ion moving to anode. Okay, we're having 2 types of negative, and they are moving to the anode, and we're having ion moving also to the anode. And we're having 2 types of positive moving to the cathode, and ion moving to the cathode. And because some types are negative, they have one too little, electron, we are moving to that one, and one some have too much, they're moving to that one. There's moving, and that helps the current to be carried. Unlike the current flowing in the wires leading to the anode and from the cathode, which is in fact a one-way flow of electrons in the wires, the movement of the ions in the electrolyte is a two-way flow. That makes sense. So the ions going basically in all directions, or in the two directions. That comes in, that goes out by, because some are plus and some are minus, some are too many electrons, some too little, and they're all splitting where they want to go. The movement of the ions in the electrolyte is a two-way flow, and this is what constitutes the current through the electrolyte. I don't understand the sentence. How can something constitute something? I think we're saying because they are moving, they're having a flow of current. That is what that means. As a matter of convenience, a current is always considering to flow in one direction in a circuit, regardless of the direction or directions in which actual charged particles are moving. A current is always considered to flow in one direction in a circuit, regardless of the direction or directions in which actual charged particles are moving. Then we're going to explain it. Long before the existence of electrons and ions was known, a choice of current direction had to be made. And it is unfortunate that the chosen direction, from positive to negative, is the reverse of the direction in which electrons travel in a metallic conductor. Okay, some time ago in the past, when we knew already about electrons and ions, we already had to make a choice whether current flows forward or back. And it is unfortunately so that the chosen direction, current flows from positive to negative, which makes some more sense. There's current, it's positive. On the other hand, there are electrons, there's electricity. The negative is the reverse of a direction in which electrons travel in a metallic conductor. A metallic conductor, so we're saying that it's a conductor, it's a sort of metal, which is conducting electrons. And in that, the electrons are moving from negative to positive. Okay. For many purposes, this is of no concern to us. The usual current direction conveys all the information we need. The usual current direction conveys all the information. Does it not flow in both directions in a cable? Or is that the big trick that not your lamp suddenly brings electricity to generators? So, when an electric current flows through an electrolyte, ions meet the two electrodes and give up their electrical charges. When an electric current flows through an electrolyte, or salt water, ions meet the two electrodes and give up the electrical charges. So the ions getting the electricity, the positives moving there, the negatives going there, they're going there and giving up the electrical charge, and wherever they have transported it. In some cases, the electrodes themselves send ions into the solution. The electrons, what are electrons? How can the electrons give ions? In some cases, the electrodes themselves send ions into the solution. So the electrodes. We have made our electrodes. Ours our anode and cathode. Two rather different situations arise as the diagram shows. Diagram A shows a voltmeter in a circuit. Okay, it is flowing, we're having a voltmeter, and where is it flowing? Some chemical changes are taking place in the voltmeter as ions are discharged. This requires some energy to be supplied, as in fact being supplied by the battery shown. What battery? There's some battery, and that brings current. Are we talking here? And as in fact being supplied by the battery shown. In this circuit, electrical energy from the battery is being converted to chemical energy. In the voltmeter. We're having electrical in the battery, and now in the voltmeter we have salt water, and because that is now moving and splitting up, we're converting it. Diagram B, where's B? Shows two electrodes in an electrolyte, and once again, ions are being discharged. This time, however, the process is supplying some energy which is lighting the lamp. The electrodes and electrolyte form a simple cell which converts chemical energy into electrical energy. The electrodes and electrolyte form a simple cell which converts chemical energy into electrical energy. We're saying we have now a battery sending out electrical energy, doing something with water by splitting it up and sending the +1 to the minus and the -1 to the plus. And with that we have made chemical changes because it was in the saltwater chemistry. And now, because the current flows now through the saltwater, it will be transported through the ions going to the both cathodes or whatever, to both electrodes. When you have transported the electricity, it goes on to the lamp, and the lamp is burning. And because the lamp is not burning, we have again electric energy. Is that what we mean? The electrodes and electrolyte form a simple cell which converts chemical energy into electrical energy. Now, I don't think we really got it, but when we read about it, and I think we will understand when it goes on down. We can follow. And maybe we can understand the bits way from there. That was the electrical engineering part. If you were here for electrical engineering, you can go directly to the next part of electrical engineering. You will do now the arm strength training. If you stay and participate in the arm strength training, then SVT armrisk. And I wanted to emphasize that, okay, if you participate in SVT armrisk, this is a bit special arm strength training. And we have 3 rules. If there's pain, stop immediately. Go on as far as you can go with a little bit of effort, it doesn't really fit. And the first rule, don't overdo it, we just want to strengthen, not to exhaust. And the bit time important here, if there's pain at the finger, stop. So the first exercise is the start. Arms long out and press with fingertips together. Have a little bit of a bend in the elbows. And again, if there's anywhere pain, especially at the fingers, then stop. And keep pressing. And now you can continue with the start, or you can do the pro, where you press just with the fingertips. It's a little bit more extreme for the fingers and for the elbows. And again, if there's pain, stop immediately. And the next exercise. Now, have the 4 fingers like that, and press into the finals, just finger and half finger. Press into the finals of the hand. Press. And open slowly up. And on the other side. Press and come slowly up. If this causes pain at the wrist or somewhere else, the finger stop. And again, press and come up. And again, press and come up. And another thing. Press and come up. And the last time. And now if we are ready around, we're taking it like that, press, and come again. And on the other side, press, and come up. And again, press, and come slowly up. And last time, press, and come. And last exercise, 1 arm out, press against it, and bend slowly. With your other hand, press, and come slowly. And again, press, come slowly. And the last time, press, and come slowly. And we're ending with stretching the Musenmaß, arms to the side, circle them. Let's do it also backwards. And let's do some big circles. Back, up, back, other way around. And with arm stretching, 1 arm in front, shoulder back and down, pull the arm in. Flat fingers, try to relax your arm, go back with the shoulder, then power to the sky. We have arm in front. Back with the shoulder down, pull the arm in, have flat fingers, try to relax your arm, go with back with the shoulder, then power to the sky. And last exercise, 2 more. First bit on the floor, go with moderate effort, moderate force over the middle part of the lower arm, and on the other side. And just with the arms up, and down, and arms up, and down. That was the arm strength training. I thank you very much, and